Hi, this is Dr. Simon Romero. I'm here to present you the video tutorial for double integrals over simple regions. Simple regions are classified in two different types, type 1 regions and type 2 regions. A type 1 region is it's also called an X region, and it's a region that lies between the graph of two continuous functions that depend on X. In other words, the thing that we're saying is that the X moves between two numbers and the Y moves between two functions that depend on X. Hence the name X region is denoting the region that actually is going to be moving between two numbers. Type 2 region is going to be more or less the same, but now Y is going to be the variable that's going to be moving between two constants. So the Y moves between two constants and X moves between two functions that depend on Y. So in other words, you can think about the variable that moves between two constants to be the independent variable, and the X, or in this case the X, that is the one that is moving between two functions, is the dependent variable. Let me tell you a little bit about the integrals over type 1 region, how we're going to integrate these regions. And the idea is going to be just extending Fubini's theorem for this type of regions. So let's say that we have a type 1 region, X moves between two numbers and Y moves between two functions that depend on X. Obviously those functions are continuous. So we're trying to compute this volume, and in order to do that we're going to do exactly the same thing that we did with Fubini. We're going to take a cross section, so fix an X, take a cross section with that X, and let's try to find a formula for the cross section. Notice that this cross section can be obtained by just taking the integral of f of xy dy, integrating over y between g1 of x and g2 of x. Notice that right now we're fixing x, so these numbers are already fixed. Once we have that, we're going to integrate this area of cross sections along all from x equal to a to x equal to b. So the thing that we have is an iterated integral, just like the one that we have right here. And notice that this is a generalization of Fubini. In Fubini's case, we have that these two were constants, and now we're extending a little bit for allowing these two limits, the innermost limits to actually be continuous functions. So the only thing you have to remember in these cases is it's going to be just like Fubini. The only thing that you have to make sure is that the functions go inside of the integral. In other words, you always integrate first the variable that moves between continuous functions, and then the second variable is the one that moves between constants. Note that the order in this case does matter. The integral over type 2 regions is pretty much the same thing. We fix a y, we compute the area of the cross section for that particular y, that is going to be the integral from h1y to h2 of y, and then once we have that cross section, we integrate over all the y's, we obtain this iterated integral. And again, you just have to be careful that the integral, the variable that you integrate first with respect to is the one that is moving between two functions. Let me give you an example. Again, the order does matter in these kind of cases. Here is the example. Suppose that I'm evaluating this integral over this region, the region that is bounded by y equal to ln of x, the lines y equal to 0 and x equal to 2. One of the things that you don't need to do, but it's always convenient to do, is to draw your region. So I'm going to do that. Notice that the line y equal to ln of x looks like this. That's the graph of this function. The y equal to 0 is just the x-axis, and the x equal to 2 is just a vertical line passing to the point 2, 0. One of the things that you have to notice is this one is either a type 1 or type 2 region. In this case, I'm going to take it just as a type 1 region because I am explicitly given y as a function of x in here and another y as a function of x. So notice that the y is moving for every x, the y is moving from the red line to the green line. So the thing that we have is that y is moving between these two continuous functions that depend on x. Once we have that, we just have to figure out what are the numbers in which x are moving between, and it's moving between the x-coordinate of this intersection point and the y and the x-coordinate of the other intersection point. In this case is 1 and 2. Once we have the region expressed as a set, it's very easy to evaluate the integral using Fubini. We just have to determine which one is the variable that we're going to integrate with respect to first. And remember that you integrate first the one that moves between functions. So the thing that we're saying is, inside we're going to integrate with respect to y, and the limits of y are going to be just the bounds on which y is moving, and the bounds of y are actually continuous functions that depend on x. The bounds for x are just going to be numbers. So once we integrate first the innermost integral, so we have this integral, that's integral with respect to y, and we're going to take when y is equal to 0 to ln of x, then you evaluate like this, and you end up, after simplification, to something that looks like this. Then we integrate with respect to x, gives you something like that, after doing some integration by parts, and then simplifying gives you this, and then you evaluate from 2 to 1, or from 1 to 2, I'm sorry, and then once you have your evaluation, it gives you that this integral is equal to minus 1 over a. The last thing that I want you to notice is that this region is also a type 2 region. The only so the thing that we're saying is now the y is moving between two numbers and the x moving between two functions that depend on y. From here we can get the function that depends on y by just solving for x. And once you solve for x, you obtain this. And the green one is the one that goes on the bottom, and the blue one is the one that goes on the top. So you could get exactly the same answer by just integrating these now in this order. Well, thank you very much.